Okay, guys, let's continue with the completing of Delaunay triangulation. This was a simple algorithm we discussed. In this algorithm, what we do, we start with a set of points and then try to find a larger circle containing this set of points P. And for that larger circle, we need to have two extra points, P minus 1 and P minus 2. And then since it's an incremental algorithm, we need to take these inputs one by one and then update our triangulation. So at any point of our algorithm, we have a proper triangulation. So what we do here, we have a random set, and then among this random set, we pick one point and then do the triangulation with it. And if you come up with illegal edges, then you need to legalize all of them. So there are two cases. Your point PR might be inside a triangle, or your point might be on the triangle. This else part is for the case where your point is residing on one of the edges of the triangle. And if you look at the details of these two parts, the if part and the else part, we have some legalized edge calls. Since once you are doing triangulation, you always generate new edges. And once new edges are generated, they should be checked whether they are legal or not. And we do it with the help of this legalized edge function. So if you have a kind of any triangulation, you can simply do legalization with this function and try to make it kind of an angle optimal one, and maybe doing a triangulation. So let's have a look at this one. This function is very important, and as you see, not complicated. As we have shown in the drawings, once you come up with an illegal edge, you simply flip it. And this function is actually doing that. It's flipping the edges and removing one edge and then generating a new edge. And that's why, since it's generating a new edge, it's calling itself inside this same function. So we can say that it's a recursive function calling all the time itself. We discussed this example, if you remember. Now we are adding a new side PR into this region, and then once you add it, you come up with illegal edges. And then you need to run this legalized edge function to make it legalize. If you continue, you will see that once you continue legalization, you will be illegalize actually some of the other new edges. So once you do that, you need to run a legalized edge function many times again and come up with such a new triangulation. If you compare these two, it's totally different, especially this part, since the rest is right now not affected with the addition of PR. Only this gray portion is affected. So now we have some lemma about the computation. So it says that every new edge created in Delaunay triangulation or in our legalized edge function with the help of the addition of PR will generate an edge of the Delaunay graph. So once you add a new edge, new side, then that means you will be adding a kind of an edge into your Delaunay graph. So now, if you consider the approach, the most important thing is actually to find the triangle in which actually you have the new point PR. Now let's have a look at this detail, how we are going to find a triangle, what type of data structure we should use for that purpose. And as you see, it suggests that we kind of use point location structure. And for that, we prefer to use directed acyclic graph. So which means that you have kind of points, and these are directed. So you can go, for instance, from top to this one, and then this one to this one. And then maybe we may have another edge here. May have such a connection also, or another connection like this. So they are all directed and acyclic, which means that it's not cyclic. You'll have some examples about it, and you will see that it's not that complicated. And in that graph, actually, we will have some leaves, like in the case of trees. And these leaves will be corresponding to triangles in your current triangulation tile. And we need to have obviously some cross pointers between the leaves and some internal nodes of your triangulation. With the help of it, you can easily determine the triangle in which actually your point PR is residing. Another important issue that is that the internal nodes of your direct acyclic graph will be corresponding to triangles which were actually leaves in some of the previous triangulations. So you start with a single data structure, you continue updating that data structure according to your addition of new points, and obviously some of these internal nodes will be modified, the cross pointers will be changed, and you will have new children of these leaves. And once you have them, you will always be considering the leaves, and the leaves will be corresponding to the current triangulation, but the internal nodes will be corresponding to the triangulation, triangulation actually you had before. You will see some examples, and I think that will be much clearer. So how are we going to construct this point location structure or directed acyclic graph? So at first, obviously, we have a single triangle, and that triangle is in between P0, P-1, and P-2. So we can say that we can start with a single node, and that might be triangle 0. And then what we are going to do, if you, for instance, at this one, PR, let's say, we will have some new triangles formed. How many of them will be formed? You have 3 new triangles. So from this one, we will have 3 children. So these are the leaves of this direct acyclic graph will give us the current triangulation. We have 3 triangles in the current triangulation once you add the new side PR. So then what we do after having these 3 triangles, for instance, this is a total different example. You have such a triangulation currently, and we have 3 triangles, delta 1, delta 2, and delta 3. And now we are adding a new triangle inside delta 1, right? So you see this is our PR, and we have now new triangles generated. So that means we are going to divide actually or have children of delta 1. You see, initially we have delta 1, delta 2, and delta 3. Now we have some children of delta 1, and delta 1 is no more a leaf of this data structure. So this is not anymore any leaf, it's an internal node. If you remember from the previous slide, we said that the internal nodes are at some point where actually the triangles in the previous triangulations. But now this is not a triangle in our current triangulation. These are the triangles in the current triangulation. And if you come up with an, let's say, illegal edge, you can still continue with legalized edge function. Here you see the example. Once you have PR here, then obviously we have an illegal edge here. This is the illegal edge. We have small angles, so we need to legalize it. And once you do legalization, you'll have delta 2 destroyed and 2 new triangles formed. So that's actually how it's represented here with the help of the data structure. Now, initially, we had delta 1 divided into 3 new triangles. And after the flipping operation, we have delta 2 destroyed, and that's why we have some arrows actually, or we have children of delta 2, and you see there are leaves of delta 2, and they also have connections to, let's say, now I will give another name here. Let's make it A, B, and C. So this is A, B, and C, A, B, and C. And you see that the new two triangles are actually children of C and delta 2. So that's why we have connections to C and delta 2. That's how it's represented. And let's have a look at the leaves. This is a leaf, it's a leaf, 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 and the last leaf. So let's check it on the triangulation. This is A, B. So we have A, B, delta 5, 4, and delta 3 as leaves of this data structure. So everything is fine. We can continue it, checking other operations. Do you see another illegal edge here?
Hocam PI/PK olabilir mi?
Yep, that's a kind of an illegal edge. You may now fix it. So as your friend pointed out, we have an extra illegal edge. This one between PI and PK. This is the current data structure for the triangulation. Now we need to update it. We are going to destroy delta 5 and delta 3 and then form two other triangles, which are delta 6 and delta 7. So these are to be destroyed, 5 and 3. So we need to have connections from these ones, right? Since the new triangle will be, these triangles will be the children of these two older triangles. So this is how we continue constructing the directed acyclic graph. So now let's have a look at once again. This was A, B. The leaves of the data structure, A, B. We have delta 4, delta 6, 7, and we don't have any other leaves. So let's check it on the data structure here, on the triangulation here, A, B, and we have 4, 6, and 7. So it is fine. We have done this triangulation and constructed data structure properly. Any questions, guys, about this data structure, about locating our points? So once you have this data structure properly always, so how you are going to locate a point? For instance, assume that your point is somewhere here. Okay, then what do? You start from the top and then continue checking these triangles, and you will find, for instance, at first, you will find that your point is inside delta 2 in the initial triangulation, okay? And then you will continue checking the children of delta 2. You will check whether your triangle is inside, your point is inside delta 4 or 5, and you will see that it's inside delta 5, and then you will continue once again and finally come up with a triangle which is the leaf of the data structure, and also it contains your point PR. So you need to continue until you come up with a triangle which is a leaf of the data structure, and once you find it, then you can stop and say that your point is inside delta 6, and you need to further do triangulation with delta 6. Any questions, guys, about how to locate the points inside using this data structure? Okay, this is what I mentioned in the previous slide. We start from the root of the data structure, check all the children, go level by level, and then try to come up with a leaf which contains your point PR. So the same things. So since the out degree of any node is at most 3, so any node can have at most 3 children. So this is not a very complicated data structure. In linear time, you can determine which triangle actually is containing your points. So what about P-1 and P-2? Initially, we said that these should be far away so that they will not be affecting the required triangulation. Since in the given set P, we don't have these 2 extra points, and we have them just to make our triangulation easier. So if you are adding extra points, then they shouldn't be affecting the final triangulation. So that's why we don't assign some values to them. We simply treat them as symbolically. So you may assign some random values or just some letters. So now let's briefly talk about the computational complexity of this algorithm. Some parts are quite complicated. We will take them as granted, but at least see the main complexity. So what we are going to do first is to check the structural changes. So in the triangulation, how we start, we have many points, and then we have 2 extra points, P-1 and P-2. We have this large triangle. Assume that this is a triangle. And then what we do, we start adding these sides randomly. And once you add it, then you form some new triangles. And sometimes once you do legalization, you destroy some of these. So in according to this algorithm, we have some triangles generated and destroyed. So the only structural changes in the triangles. We need to take care of actually consider the number of triangles created and deleted. If you find a proper, let's say, a maximum value or a relation with the number of sides and the number of triangles created and deleted, you can simply state the complexity of the algorithm. So we have our number of points, and then what we do, we construct the graph, the Delaunay graph, first by adding 2 extra points. And now we have some lemma related with this analysis, time analysis. The first one is the expected number of triangles created by the algorithm. We discussed the Delaunay triangulation is at most 9n plus 1. So at most, if you are given n number of sides, we can at most generate this number of triangles. Creates. So we don't say that that will be the final number of triangles, but during your computation, this is the maximum value you can create triangles. And if you look at it here, it's obviously has a linear relationship between the number of points and the number of triangles generated. So how we determine it, let's consider the details. Once you add a new point to your triangulation, you may split 1 or 2 triangles. So if that's the case, then that means you are generating 3 or 4 new triangles. If you look at these 2 cases, if you remember them, for instance, if your new point is here, you will be creating 3 new triangles, right? But if your PR is on the common edge of 2 triangles, then you will be creating 4 new triangles, so 2, 3, and 4. So there are 2 cases, and In one of them, you create 3, and the other one, you create 4 new triangles. Another case, if you do legalization, for instance, consider the flipping operation. What do? You create 2 new triangles. So these are the ways, actually, the only ways you can generate new triangles. Now let's consider some details related with the generation of new triangles. Once you add the new point PR, then you will be adding actually new edges to your side PR. Then you can create at most, this is given here, 2 times K. K is, by the way, the degree of the point PR. This is the maximum triangles you can generate, 2K minus 3. As I said, K is a degree of PR, and degree is actually the number of edges your point can have. For instance, this one has 2, 3 degree, 4 degree. So depending on the degree of the new point PR, you can determine how many triangles are to be generated. And according to another theorem, actually, right now we are taking it as granted. The expected degree of a random point and the triangulation is at most 6. It might be less than that, but generally, in average, it is 6. So that's why now if you do some computation, you will come up with the final equation 9 plus 1. So the expected degree, this is the expected letter for abbreviation of that. Now we are trying to determine the number of triangles created in any step R. So what is the degree? The expected degree is 6. So if you multiply 6 and subtract 3, you'll come up that it should be less than 9 for any point R. Since we have n number of points, we will repeat this generation for n number of times, so we need to multiply it, and we have an extra triangle around, so that's why we have in maximum 9n plus 1 number of triangles generated in this algorithm. Any questions, guys? So this is just summarizing the time complexity of Delaunay triangulation. If you have n number of points, it states that the triangles can be completed in linear arithmetic time and linear expected storage. And this is also expected. It's an average time complexity. And this is again an average storage. Right now, we didn't discuss how this linear arithmetic case comes. We will take it as granted in a moment. And we have a linear storage since we only have a kind of an structure D, direct acyclic graph. It depends on the number of triangles created. Since the number of triangles created depends on the number of inputs, so we can easily say that is in average it depends on the number of inputs, and we have a linear storage complexity. But we didn't actually consider the time spent for point locating. So you have a new point. So how much time are you going to spend to locate your point inside this data structure? We didn't consider it. If you assume that this is not important, then we can simply say that the time complexity of your approach is linear. But obviously, we will be spending some time to find these triangles where your new points are residing. And this is actually stated with an other theorem. We will, as I said, take this as granted. This is actually about, this has a proof in our textbook, but it's very complicated and quite long. If you are interested, you may have a look at it. This is the cardinality of the circles you are generating around the sides. For instance, you have such a side, and this is another circle. So that is a circle. You'll be checking if you have any points inside or not, depending on it. That will take actually a linear arithmetic time, and we will be using this part actually in our time complexity analysis. So that's why we will say that our overall time complexity is limited by linear arithmetic time. In classes, guys, up to now about the computation and the analysis, I skipped some of the parts of the analysis. It's quite long, as I said. If you are interested, you may have a look at the textbook. If you don't have any, let's try to finalize this chapter, conclude this chapter. So we are using these triangles in different fields of science. We can do numerical analysis, finite element analysis. These triangles can be used in different ways. In computer graphics, you can represent shapes with the help of these triangles. You can represent terrains or other even 3D objects. And another thing we actually come up with inside this chapter is that once you have a triangulation, then by doing some flipping operations, you can obtain the other triangulation. So this is stated by Lawson. And in addition to that, if you remember, we were always trying to find an angle optimum triangulation. But depending on your cost function, you may have other triangulations, and that these triangulations may be better for your application. So in such cases, you need to define the cost function properly and then update the algorithm accordingly. And these are not that important. For instance, in a kind of an cost function, you may have minimum weight triangulation. You may try to decrease the length of the, let's say, edges. This is another way, but it's somehow related with the angle optimum case.